I've been researching radar systems together with my colleagues Professor Bernie Mulgrew and Dr. James Hopgood at the University of Edinburgh School of Engineering. In a nutshell, the aim of a radar system is to estimate the bearing angles of one or more targets with minimum error as quickly as possible. One way to improve on the current technology is to use a cognitive radar algorithm we have developed to adaptively shape the beam such that the error is minimised. This is also referred to as adaptive waveform design. Although our primary focus has been cognitive radar, from a technical point of view, the algorithm we have developed also applies to other active sensing modalities such as sonar. To explain how our adaptive waveform design algorithm works, consider a cognitive radar system estimating the angular location of a single target. Initially, we do not know where the target is, so we transmit a waveform that is uniform in all directions, shown here by the radar beam pattern in black. We can interpret the received reflections from the target of this initial uniform transmit waveform as a probability of the target location. This gives us a statistical estimate of the target location. Our algorithm tells us how to design the next transmit waveform given this statistical target location estimation, such that it improves future estimates of the target location. Observe that this waveform is no longer uniform. Again, the reflections from the target of this transmitted waveform can be interpreted as a probability of the target location. And Bayes' law tells us that the statistical estimate of the target location is this probability multiplied by our previous target location estimation. The resultant statistical estimate is shown here in red. Once again, we use our adaptive waveform design algorithm to design the next transmit waveform given the estimation. From this simple example, we can get a sense of Bayes' law and our adaptive waveform design algorithm iteratively acting to estimate the target location and adaptively design the waveform. Ultimately, this enables the target to be estimated more quickly than a non-adaptive system where a uniform waveform is used throughout. Once again, the transmit waveform is shown in black, and we start again from the initial uniform transmission. Observe the estimate region of the target narrowing and the transmit power predominantly being transmitted in this direction. Although sometimes power is transmitted in different directions, possibly if the algorithm is trying to eliminate a remaining slim possibility of a different location. Finally, the designed waveform pattern resembles a steered beam as the power is directed to the region in which the algorithm is now virtually certain that the target is located. And we can see that the grey estimation region narrows down considerably. The effectiveness of our algorithm can be expressed in terms of the number of transmissions required to locate the target. In our example, our adaptive waveform design algorithm requires 15 transmissions to locate the target, whereas a non-adaptive system requires 13 transmissions. It's also worth comparing to an alternative adaptive waveform design algorithm, which to our knowledge is the only comparable method and takes 25 transmissions. Having proven the principle of our algorithm, our current work is focused on demonstrating its performance in a physically representative setting. To this end, we have demonstrated that our algorithm also works well for the more realistic scenario in which the radar tracks multiple moving objects.